Okay, so we have formulas for mean and standard deviation. I kind of already addressed these, so we really just have one more thing to talk about. Okay, you guys, so we're going to kind of examine this on the what is the probability that the probability that x equals 0, where x equals number of defective. All right, so in this particular setting, guys, let's go through the, let's go through this through all those different settings. Let's start with binary. Is this a binary thing? Yeah, they're either defective or they're not defective, yeah? Do we have a set number of trials? Yeah. What's our set number of trials? Nope, because we're just selecting a sample of 10 of them. Okay. Do we have the same probability of success each time? We're gonna have to look at this a little bit differently. You guys, if I know that 10% of the dials are defective, how many defective dials are there in this particular batch? 1,000. Everybody good? All right. So I've got my 10,000 CDs, right? What's the probability that the first one I pick for my sample is defective? .1. What's the probability it's not defective then? 0.9. So since we're going none are defective, let's go ahead and say, are you guys with me that we would essentially be doing 9,000 over 10,000 for the first radiodial I'm picking out? Okay? All right, I've taken that one out, and we're going to go ahead and assume that it's not defective, right? What's the probability the next one is not defective? Is it 0.9 again? Why not?
Because you took one out.
Because we took one out. So instead, it works out to be 8,999 over 10,000. Not over 10,000. Everybody with me? Now, you guys. If I asked you to approximate the value of this fraction, what would you say? The value of this one is 0.9. The value of this one is, give or take, 0.9. You guys with me? Is this exactly 0.9? No. But is it super close to 0.9? Yes. Okay. What's the probability that the third dial I pick is not defective? It is 8,998 out of 9,998. Is this making sense or no? And then the next one. And then you guys, the last one would be 8991 over 9991. You guys okay with how I'm kind of getting these fractions? Okay. You guys, I got the value of this last fraction to be nope, I have an extra 9 in there. Guys, how many of you are okay with saying, even though that's not equal to 0.9, in broad perspective, are we okay with calling this 0.9? Okay. All right. So, basic premise is whenever we are sampling without replacement, it is not a binomial setting. Is this okay? However, yeah, we don't have the same probability of success each time, but it's fine, right? It's fine. Because the difference between doing this times this times this times this times all that stuff in the middle times this and doing 0.9 times 0.9 times 0.9 times 0.9, they're pretty darn similar. Is everybody with me? Okay, so here's what I would like you guys to do. You guys are going to find the probability using the binomial distribution. Is everybody good? I'm going to find that probability using some fancy math techniques. By the way, the answer to this is so hard to calculate that your calculator can't do it. I'm going to have to use an online presence to do so. But I want you guys to see that the probabilities aren't quite the same, but they're pretty darn close. Cool? So you guys do the binomial version of it. I'll do the fraction multiplication of it, and then we'll compare our answers. Just so you guys know. I got a 0.3485. Did you guys get pretty darn close to 0.3485?
3486.
So we're going to be okay with. There are times, and I'll go into more detail about that tomorrow. Nice job today, guys. All right, so if I'm remembering correctly, we didn't quite finish out the example we were working on the end of the day yesterday. So let's kind of where we had we kind of calculated everything, but we didn't kind of come to the final conclusion that we need to come to. Okay, so just this wasn't binomial because we were sampling without replacement, so that probability changed with each selection. Remembering this correctly? Okay? And so you guys did it using the binomial distribution anyway, and I did it using the actual fraction multiplication. And what do you guys think about the binomial probability versus the actual? Are they pretty darn close? Okay? So that independent condition for binomials is definitely, it's supposed to be independent, and we kind of have a rule that we can follow that says, hey, even if it's not perfectly independent, there are some situations where it's probably okay. All right? Now, this was, we took a sample of 10 and ended up with this fraction, yeah? If I had taken a sample of 200, the value of this fraction would be significantly different, yeah? And in fact, the larger the sample I take, the further and further this last fraction would be from the actual 0.9 that we're trying to model, that the binomial would model. Okay, so for this independence thing, which we need, right, to use the binomial distribution, that independence thing can apply when we sample without replacement as long as our sample doesn't get too big, right? Again, this is close enough to 0.9 that we were fine with it. But if we had a bigger sample, it'd get further and further from 0.9, so the binomial calculations get further and further the larger the sample size. Okay, so we typically say if the sample size is small enough, we can still assume independence. Okay. And the general rule of thumb of how small is small enough is if your sample size is less than 10% of your population. Then even if you're sampling without replacement, technically not independent, but close enough, we're not worried about it. Okay? That's going to come up a lot in units 5, 6, 7, 8, and 9. So the 10% condition is what we call it, and the whole idea is if our sample size is small enough, then the population isn't changing too much that we're okay with still using a binomial representation. Okay, so that was binomials. Let's shift into geometric random variables. All right. How many of you guys have played Monopoly? What happens when you land in jail?
Like when you go to jail or you're visiting?
You land, like you go to jail.
You have to roll doubles.
You have to roll doubles, right? And so like if you get doubles on the first turn, you're done, right? But if not, you have to wait another turn, right? So how many on average do you have to roll until you get doubles? Well, yeah, in Monopoly it's only 3 times. But you know what we should do? You guys think I'm going to make it?
Based on past.
Based on past performance?
No.
You guys notice I have a success now.
You're on a streak.
I'm on a streak? Yeah. You ready?
Oh.
How many shots?
5.
Who said 5? That's the most optimistic number anybody has ever given me.
Why do you do it backwards?
Because I'm just, sometimes I'm trying to make you guys smile and teach you at the same time. It's working out really well. You ready? This is not going to work.
But if it
Oh,
it was really close.
That's the best one.
Okay, so if I face it, you think I'll do better?
Yes.
Yeah.
I significantly disagree with you. I know, I look about as graceful. You guys, if it were a frisbee, I could land it in there over and over and over again, okay?
You Yeah. Oh. I was gonna make it. That was 5.
That was 5. You were wrong.
10. 8. No. Yeah, 8. Right? 12.
So you guys, hold on, just because they're going to make fun of me next period. They didn't count my first success because I couldn't remember which class it was in. The 7th period class, they like to make fun of me a lot. And you know what? I'm going to learn. Why am I throwing these away? We're going to do the same thing in 7th period. You guys will witness that I made it on the 6th shot. Yeah? They don't trust me, and I think it's unwarranted. But hey. All right. So, you guys, let's talk about this. Did we still have repeated trials? We still had repeated trials. And were those trials binary in nature? Okay, cool. So, on that particular trial, our x equaled 6, yeah? If I did this again, is it going to take 6 tries?
Maybe.
Maybe. It could. Oh, that was bad. Oh, I thought that one was in.
Does it count if it's in the recycling bin?
I mean, theoretically, we would hope I'm aiming for the recycling bin because they're recyclable. But I'm going to take either because I need all the help I can get.
Your 4th try?
4th try. And if I did it again, we're going to keep having lots and lots of tries, yeah?
Are you sure, though? I think we should try again, just to see.
Is that not your first try?
Oh, wow.
You have your strategy.
So that would be x equals 1, x equals 1. Yeah. But you guys get the basic premise, yeah?
You should count this under your success. Good. But just the first 3 tries.
1, 2, 3. No, that was 3 successes and 2 failures, yeah?
Yeah.
There's no way they're going to believe this. You guys, if you see anybody from my 7th period, which is, the squirrely boys, tell them I got 3 in a row. They won't believe me if I tell them. You know what I'm saying? Like if you see Blake or Kenny, or does anybody have classes with them next period by chance? I have 7 Teddy in there. Yeah. They're the ones. Luke Stanley. Those are all the ones that tend to give me a hard time. Yeah. Okay. So binary check. Hey, was each throw independent? But now, what did these variables stand for? What was this x?
Number of tries.
It is x is equal to a number of trials. So, one of the hardest things that you guys are going to have to start figuring out is, now that I'm mixing geometrics, and you're going to have to decide between, is this a geometric versus a binomial random variable, okay? And binomials are x is a number of successes within a set number of trials. Set number of trials. Geometrics, we don't have a set number of trials. And the variable is the number of trials we need until success, or the number of trials until the first one, okay? Keep the words until and first are good signal words too that you should be using the geometric probabilities instead of the binomials, okay? And do we have the same probability of success each time? The probability that I'm going to make it is the same every time. Though, if you guys wanted to make the argument that I got into a groove there at the end, I would listen to say that maybe I've improved.
Or you were friendly at first.
Yes. You guys, we all learned that the bank shot is way better shot for Miss Meister than trying to do a swish, right? Okay. Now, the formulas for the mean and the standard deviation of geometric variables are on your formula sheet. The mean is 1 over p. So, for example, if I was a 20% shooter, which is what it's starting to look like, right? It's roughly 20%. A little bit better than 20%. A little bit, right? If I were a 20% shooter, how many would you guys expect me to take each time? 5. Am I a 20% shooter? We don't know. You guys with me? Why, thank you. Oh!
Now you are 20%.
Mm.
Right?
It's still a little bit short.
Oh, I thought that was.
Yeah. All right. Let's go ahead and just do some practice questions here. So let's go ahead and say I have 2 dice. I'm going to keep rolling until I get doubles. So this is not Monopoly dice. This is just in general. We're going to talk about the Monopoly decision making in a second. Okay? So if I'm rolling until I get doubles, show that it's geometric. That means, the first thing, binary. Is it binary? When I roll my 2 dice? Because we're recognizing doubles or not doubles. Cool. And independent? One roll doesn't affect another, right? Cool. My variable is essentially how many rolls does it take. Okay. Do I have the same probability of success each time? What is it? Continue to explain how you got to 1 out of 6.
So it's like guaranteed you'll roll like one of the first die.
The first die doesn't matter. Yeah, because you're basically saying what is the probability that the second one matches the first one. Cool. It's a Friday where we seem to be in a smiling mood. You guys want to count how many times it takes you to get to a doubles? The left hand is so... All right, so Riley was a 4. 2? 5? 10?
12. 8.
9.
10? 5?
13.
Woo. Is that everybody? She's not my Monopoly partner. 19? Was it 6? 6. 7, 8, 9, 10. Now, if we did this all again, is Freya going to take forever next time? Maybe. Maybe. And likewise, Skylar, you were the 2, yeah? I bet it takes you more next time. Yeah. All right. Is anybody shocked to see the way these numbers kind of shake out? And in fact, let's draw a quick if you had to guess the mean of this, what would you guess it to be? Give or take? Tell me where I hit the balancing point, yeah? Right about here? I'm going to call that 6. Are you guys comfortable with that? About 6? Guess what? Now, how many would you expect to get? Well, that would be using the mean, which was 1 over p, which is 1 over 1/6, which is 6. And our graph kind of supports a mean of 6 on this, doesn't it? You guys. If I say what is the probability that t equals 3, are you with me that it takes exactly 3 rolls to get doubles? Is everybody with me? That's what that would mean? And if I asked you guys to find that, these ones don't have a super complicated formula. Okay? It's not super complicated. What would need to happen on the first roll? You don't get doubles, and the probability of that is 5, 6, yeah? What would need to happen on the second roll? Third roll? Get doubles. So 25 out of 216, which I'm sure has a value. Riley's like calculator whiz over there. 0.115. 0.116. Great. You guys, remember using the calculator to go into that binomial menu yesterday? Look just underneath the binomial, so you're going to hit second vars. And then we know this is a geometric random variable. Do you guys see anything in that vars menu that might help us with geometric random variables? Oh, there's a geometric PDF and a geometric CDF. Yes, given this one and what we learned yesterday, which one should we pick? PDF. Okay. For those of us who weren't here yesterday, why PDF? Because the PDF does whenever something is exactly equal to. Okay? So notice when I choose the geometric PDF, it doesn't ask me for a number of trials. Why doesn't it ask me for a number of trials? Because that's the variable. We don't know how many trials. We're trying to figure out the amount of trials, the probability of a specific amount of trials, yeah? Okay, so P equals 1 out of 6, I think. And you know, yesterday we were putting in decimals. You can put in the fraction, that's fine. My x value is 3. Guys, I got 0.11574, which I bet is pretty darn close to what Riley got. 0.116 is where it rounded, yeah? Everybody good? Okay. So Monopoly, you get out of jail by rolling doubles within 3 turns. What is the probability you get doubles within 3 turns? Huh? That would be the probability is less than or equal to 3, yes? What does this make you want to do in your calculator? CDF, yes? Now, yesterday I made you write down a whole bunch of stuff. Today I'm going to make you write down a whole bunch of stuff. Okay? What was the name of the distribution we used? What do we pick in our calculator? Geometric. So this is the geometric distribution. Has the CDF been communicated yet? With the less than sign, right? Has the P been communicated? Has the X value been communicated? That's all I need. Okay. Now, the College Board loves to give questions like this one. Where there's a mix of a lot of different things going on. Okay, so let's go ahead and look at this. In a series of professional soccer player succeeds in scoring a goal on 84% of his penalty kicks. Assume that the success of each kick is independent. Cool. So, what are some key ideas here? What are some things jumping out at you about the question of this?
Asking for when he fails.
Is asking for when he fails. Okay. So are you with me that our variable in this case is the number of shots until a miss? And is this a situation of repeated trials? And what is a single trial? Every time he shoots on goal, yeah? Every time he takes PK. So, binary, yeah? Independent. Do we have a set number of trials? No, because we don't. The variable we're looking at is the number of trials. So what does that tell us? This is a geometric, for the one of you in the back that never says it out loud but always mouths it to me. Everybody good? All right, so if this is a geometric variable, how am I going to define P? P is the probability of success on any given trial. And as I say this, how have we defined success with our variable here? A success is a miss. You guys with me? Okay, so you guys with me that my P would be 0.16? My probability statement might look like the probability X equals 5. Everybody good? And I feel like I have enough information that I know what to do in my calculator. What are we getting?
0.0797.
So 080. That's how that would round. Everybody good? Okay. What would change for part B? X would be 3 shots for sure. And now X stands for number of shots
Until you make it go.
until a make.
So then P would be 0.4.
And the big difference then would be P equals 0.4. So, and by 0.4, I mean 84. I don't know what I was thinking. Just thinking about taking shots at the waste paper basket. I don't know the answer.
Oh, 215.
0.2105?
Or
Is that what you guys are getting?
0.021.
Oh. Better? Cool. Huh?
Would be 225.
Do you guys think I could take this, bounce it off of Eleanor's head, and into the trash can? I think the laws of physics would prevent that from happening, but it would be sweet if I could do it. It's like one of those, like, if you had somebody in a green suit and we could film it happening and then edit them out. All right. Hey, you guys, what about this next one?
Is there a certain amount of decimals you usually?
Nah. Whatever I say. I like to make you guys predict what I'm thinking at any given moment. 3 or 4 is good. Okay. Are you guys? So if I were to ask you to fill out this part first, what would I put inside here?
X is less than or equal to 5.
X is less than or equal to 5. Everybody good with that? And in this case, what does X stand for?
Shots until he stops.
Mm-mm.
Shots until he misses.
5 of his next 10, yeah? So X is the number of scores. What else has changed? We have a set number of trials now. And since we're defining X as number of scores, our P is going to be 0.84. So, when I look at this gives me a lot more information. What should I pick on my calculator? Binomial, because this is now a binomial distribution, because we have a set number of trials and X is a number of successes. And we'll use binom CDF, right? I don't know the answer. I know it's a relatively small number.
0.013.
Okay. Suppose our soccer player is out of action with an injury for the next several weeks, okay? And then he goes on and takes 10 penalty kicks and he only scores 5 of them. Now, how many would you expect him to score if he's 84% successful? 8, maybe 9. Yeah? Okay. And he only got 5, which is a lot lower, right? Do you guys think the injury has changed his ability level? What if he had only made 7? What if he had made 7 instead of 5? Would that convince you that the injury? So why is 5 convincing to you guys that the injury has affected his ability level?
Very unlikely.
Because it's very unlikely. Yeah? Remember how we started talking about statistically significant, right? Like if 2 treatment groups are like here, not very convincing, but here is very convincing. Same idea. Okay? And it always comes back to probability. The probability that regular, good, healthy guy could make 5 or less shots is less than 2%. You guys with me? Okay. So, the answer is definitely yes. It's very unlikely that he makes 5 or less. Right? We're done with probability. That's not to say that